Welcome to this course Applied Thermodynamics. We are in the module 3 internal combustion engine. Till date we have covered about 8 lectures. Today we are in the 9th and last lecture, and this title of this lecture is Exergy analysis and engine emission and pollution. So, under this heading we will try to find out some thermodynamic aspect with respect to evaluation of energy, and here this evaluation of energy we will interpret in terms of exergy with thermodynamic viewpoint or concept of available and unavailable energies. In the other segment we have engine emissions and pollutions. Under this heading we will mainly concentrate hydrocarbon emission, carbon monoxide emission, oxides of nitrogen, solid particulates and emission index. So, let me start with the first topic, that is evaluation of exergy. Till date we have given the attention of IC engine topic mainly with respect to applications and with respect to engines, with respect to its performance, with respect to thermodynamic cycles. Now, in this heading we will try to see how much energy we are going to waste, or in terms of available energy of the fuel, how much energy we are going to recover, or is it possible to recover, or is it a irreversible process, so that none of the energy can be recovered. And we also seen in the last class in our heat transfer study, we found that only 30% of the fuel energy, 30 to 35% of the fuel energy is getting utilized, 30% of the energy goes as a heat transfer to the different medium, and rest 30% goes as a waste heat in the mainly in the exhaust. And in fact, our attention is last 30% of the energy which goes as a waste, and in fact, this is the unrecoverable energy, and if attention is focused, then we can tap some amount of the energy. Now, in order to estimate that calculation of energy, we are now going to study the exergy for engines, and we will try to focus mostly in the exergy in the exhaust of the engine. So, let me give some introduction to this topic of exergy. Estimation of available energy determines the maximum possible performance of a thermodynamic system. In fact, impact of process change in the system in terms of losses are also assessed. The exergy analysis provides the knowledge of how the available energy is lost or destroyed in the engine system. In fact, these findings will help us in reducing exergy loss to improve the performance of the engine in terms of efficiency and power output. So, in IC engine operation, the exergy analysis reveals two aspects, and mainly the energy destroyed due to thermodynamic irreversibility. So, in this case we have the combustion, heat transfer, mixing, throttling, friction, etc. Other aspect is energy lost due to undesirable transfers. So, if you look at the schematic of the thermodynamic system, we can say this is our engine, and this engine can be treated as a closed system where there is no outside work, or there is no heat transfer other than the energy from fuel and air, and from this engine we get the shaft work output, and finally we get the combustion outputs, and in this combustion product goes to atmosphere. Okay. So, obviously, if you are releasing these combustion products at a higher thermodynamic states in terms of temperature, then obviously we are losing most of the heat, and in fact this is what happens in the engine. So, in IC engine the exergy input is contained as chemical exergy of the fuel that is converted to the other form. This exergy transfer is mainly with respect to shaft work output, the exergy transfer with respect to cooling water, exergy transfer with respect to exhaust, and unaccounted exergy destruction or irreversibility due to friction, radiation, heat transfer to the surroundings and operating auxiliary components. Now, these system loss data are used to develop an explanation of why engine performance is changed by the variation of design and operating parameters like speed, type of the fuel and load. So, in fact, if you try to correlate this particular schematic figure which is a engine and closed system, we can view it as a piston cylinder device where from the intake valve the charge enters with certain quantity of heat, and through the exhaust valve the combustion product goes out. Now, when it goes out it carries lot of heat, and main intention is we are going to tap this heat, and in the process of this motion in the piston we are going to produce the shaft work, and in the entire volume we say it is a engine and it is a closed system. Okay. So, for this particular model we are going to study how we can think of exergy calculations. So, let me give some background of exergy. Exergy is the maximum theoretical work that is obtainable from an overall system considering the system and environment when the system comes to equilibrium with environment or system goes to finally it goes to dead state. So, when we refer this environment it appears as a dead state. I mean that till that point of time we can extract the energy. In IC engine it is possible to quantify exergy from the exhaust gas, and for that exergy we are going to make certain assumptions. So, those assumptions are the gaseous combustion products are a closed system. Okay. So, it is a closed system. The combustion products are modeled as air behaving ideal gas. So, we take an assumption with ideal gas with air as our one of the because this combustion product you can say mostly assuming air as an ideal gas, and just to give an estimate we assume this combustion product to be mostly concentrated with air, although the combustion product contains lots of emission products such as carbon dioxide, carbon monoxide. Apart from that we take their properties closer to the value of air. The effect of motion and gravity can be ignored. The dead state of the environment is fixed at atmospheric, that is 300 degree Kelvin and close to 1.013 bar, and because of this exergy modeling we can think that the IC engines can be upgraded for its applications when they are using a turbocharger. Why? Because this exergy calculation will tell us that the gas discharged directly to the surroundings have the potential in developing work which is supposed to be wasted. So, by venting these gases through a turbine some work can be developed. So, as you can see by tapping this exhaust gas from this turbine we are introducing a compressors where the heat is utilized in preheating the intake charge, and such a concept we call this as a turbocharger. So, the word turbocharger concept came into the engine to improve the thermal efficiency, because it is seen that the exhaust products have quite large potential in delivering work in terms of exergy or exergetic work. Now, to do this particular model, we are now revisiting a simple closed system. In this closed system, this heat and work interaction is possible with this environment. In our case, this closed system is our engine block or engine, and that is, of course, ideally it can the system can interact with this environment either in the form of heat or work, and there is a system boundary. And of course, when you say this environment has its own boundary, which is T 0 and which is at temperature T 0 and pressure P 0, and this boundary of the overall system is constant. So, what we can say, the system boundary can change, but the overall boundary does not change, and there is a possible work transfer, that is W c is possible. But our case we will mainly concentrate this particular area, which is the closed system, and with respect to engine perspective we are going to calculate the specific exergy. So, this specific exergy when you calculate, first we have to think that what is this total energy content of these closed systems. So, they can be written in three forms. One is in terms of internal energy, other is in terms of work, third is in terms of heat, fourth is in terms of kinetic energy, and fifth is in terms of potential energy. And here U, V, S, these are the internal energy, volume and entropy of the any arbitrary system, and when you put the subscript as 0, so they represent the dead state. So, in all we can say the total energy or exergy can be calculated by taking their differences. So, this is the thermodynamic expression for exergy, and in many instances if the system is at dead state and it is at rest relative to the environment, the value of potential and kinetic energy changes are 0. So, these terms can be neglected, and this is one aspect, and in our case in IC engine also this is true. This particular thing when you represent in mass basis, so we write it as small e, and all these capital terms is replaced with small notations u, small v and small s. So, this is how the exergy is calculated mathematically for a thermodynamic system, and in later point of time we will see that how this equation can be utilized to calculate for exergy for an engine. Now, let me move to the next segment, that is engine emission and air pollutions. So, in IC engine when you see engine emissions, these are the undesirable features that comes out in the combustion products, and these are mainly hydrocarbon, NOx, that is nitrous oxide, and carbon monoxide. And we have seen exhaustively that during the combustion process under certain instances, that means the engine runs with a variation on in the rich and lean mixture. So, accordingly these numbers or their relative importance is different. For example, when you have a rich mixture, we have sufficient fuel, but not enough oxygen. In other way, when you have lean mixtures, we have sufficient oxygen, but not sufficient fuel. In such cases, the products that comes out takes the advantage. So, In this case, the emissions that are of our concern are hydrocarbon, carbon monoxide, oxides of nitrogen, sulfur and solid particulates, and these are mainly in solid particulates. It mainly appears in the CI engine. Why we look for these engine emissions? Because they are threat for global warming, acid rain, smoke, odors and other related health issues. So, this particular figure shows the variation of different emissions with respect to equivalence ratio. So, we can see that a fuel rich air fuel ratio does not have enough oxygen to react with all carbon and hydrogen. So, both hydrocarbon and CO emission increase. Hydrocarbon emissions also increase at very lean mixture due to poor combustion and misfires. The generation of nitrogen oxide emissions is a function of combustion temperatures. So, it is greatest in near stoichiometric conditions when the temperatures are the highest. Peak NOx emissions occur at slightly lean conditions. So, you can see here slightly lean conditions the peak NOx of emissions occur, where the combustion temperatures are high, because there is excess oxygen to react with nitrogen. Now, let us see individual ones. First thing, hydrocarbon emissions. So, hydrocarbon emissions means it is symbol is Hc. So, this exhaust gas living in the SI engines as contains about 6000 ppm of hydrocarbon components, which is equivalent to 1 to 1.5% of the fuel. So, this means about 40% of them are unburnt gasoline components and rest are partially reacted components. So, there is a non-equilibrium situation that happens during this combustion process, and some components they crack or they break, other molecules they could not be broken because they do not get the adequate environment. But in other ways, if you look at CI engines, they operate with overall lean mixture or lean equivalence ratio, and they have only 1/5 of hydrocarbon emissions. The hydrocarbon emissions into atmosphere act as a irritants, odorant and react with atmospheric gas to create petrochemical smoke. So, this is of course, it is not advisable to have this. So, the possible causes of hydrocarbon emissions are the non-stoichiometric air fuel ratio that we have seen, incomplete combustions, Screvi's volume, that means if you will see that around the piston there are the piston and when the piston slides in the cylinder, there are piston rings that actually comes in the contact. So, those volumes, so those areas occupy some space we call as Screvi's volume. Then we may have leak past exhaust valve, there may be valve overlap, there may be deposits in the combustion valve and there may be oil in the combustion valve. So, all these things are the possible sources of carbon hydrocarbon emissions. Now, we will move to carbon monoxide emissions. So, we can see that actually the carbon monoxide is a colorless, odorless, but it is a poisonous gas and it is generated from the engine when it is at fuel rich situation, and it is mainly predominant during starting and the acceleration phase. When there is not enough oxygen to convert all the carbon to CO2, then the fuel does not burnt while some of the carbon ends up with CO2. So, ideally the combustion reaction is to be complete. If it is incomplete, CO does not go back to CO2, rather it remains as it is. But when this CO finds a adequate environment of combustion, it can react with oxygen to form CO2 and heat. Now, if this particular ambience is can be created, then it is better for the engine. Next we will see oxides of nitrogen. So, exhaust of an engine can have up to 2000 ppm of oxides of nitrogen, and most of them are in the form of NO or NO2. So, in addition to that, the temperature in the engine is also very high, in the range of 2500 to 3000 Kelvin. So, because of these temperatures, there is a very likely situations that dissociation can happen. Now, what are the possible source of dissociation that could be possible? First thing is that if the nitrogen which is there in the already in the air breaks to 2N, oxygen molecules goes to oxygen atom, and when they have their own atom, then other possible reactions could be O plus N2 becomes NO plus N, O2 plus N can possible to be NO or O. In fact, if you have hydrogen, it can come back to OH plus half H2. Even nitrogen can react with this OH to form NO plus H. Then NO plus O2 also can react with to form NO2 plus O. Then NO and H2O can also react to form NO2 and H2. So, these are the possible reactions that could happen in a temperature range somewhere around 2000 to 3000 Kelvin. Of course, it is not necessary that all the reaction will happen, but only choice is that when they get an adequate pressure and temperature conditions, appropriate reactions takes place. Of course, these reactions are beyond the control of the users, but let us see that how we can see maximum NOx, which is formed at slight lean equivalence ratio. So, when you look at the formation of maximum NOx, it is formed at slightly lean equivalence ratio, and the excess oxygen, because there are excess oxygen, they can combine to form NOx. Of course, the NOx released from the exhaust react with atmospheric gases, and they become major cause or formation of petrochemical smoke. That means, when you have, why we say it is a threat for the environment, because when you have NO2 formation from the engine, they go to atmosphere, they get energy from the sunlight, they again break to form NO plus O, and there is smoke. And this smoke, and when you have a single atom of oxygen, they can react with O2 to form O3. Of course, this monoatomic oxygen is a highly reactive, and it can initiate many reactions. So, one of them is the formation of ozone at the ground level, and this is very harmful for lungs and biological tissues. So, first effect we have smoke, other effect we have this ozone depletion, ozone formation at ground level. Of course, ozone formation at higher atmosphere is a great advantage, but ozone formation at the ground level is a threat for human health. The next category of emissions are solid particulates. That means, here we mainly see that this is the exhaust from the CI engine, and normally the solid particulates are the main sources, and they are called as carbon soot particles, and they are formed or generated in the fuel rich zones within the engine cylinder. They are seen as heavy exhaust smoke emitted from the trucks, locomotives during acceleration uphill from a stop. About 25% of the carbon in the soot comes from the lubricating oil components that vaporize and react during combustions. So, basically how the soot particles arrive in the exhaust, we can see they are mostly comes from the lubricating components, and the maximum density of these particulates are seen when engine is at wide open throttle. That means, in engine the engine is that means the throttle is almost or close to full open. So, it is a wide open throttle condition, because you are allowing more and more fuel into the engine system, and these soot particles are nothing but the cluster of solid carbon spheres. So, their size is about 10 nanometer to 80 nanometers, and these particles you can see in mostly in the exhaust of the big trucks, and they are mainly blackish in color, and a single soot particles, one can estimate that in single soot particle can have 4000 such carbon spheres of diameter 10 nanometer to 80 nanometer. The solid particulates, that is the carbon spheres generated in the combustion chamber, why they are formed? Because they do not find enough oxygen to convert all carbon to CO2. So, this is how the typical reactions that occurs when a hydrocarbon reacts with a oxygen or air. So, first one says about reaction with oxygen, where you can see formation of CO2, H2O, CO on soot particles. The other way is that we can see that similarly when you have we have CO, we have carbon soot particles, all these formations comes because this COS all this formation comes when it is engine runs in non-stoichiometric conditions, and these solid particles can react also with oxygen to form CO2. Say particulate generation can be reduced by engine design, control of operating conditions, because it creates adverse results such as increasing NOx and HC. So, for that purpose we need to have a very proper engine health management system, and they are designed to minimize NOx, hydrocarbon, CO and particulate by controlling ignition timing, ignition pressure, then also valve timing. And lastly, we will see that how these emissions are quantified. So, we have studied there are the most important emissions are NOx, CO, carbon monoxide, hydrocarbon and solid particulates. And to quantify this, we can represent a mathematical expressions by specifying them as specific emissions, which is represented as gram per kilowatt hour. So, one way is that we can specify emissions with respect to brake power. So, its unit becomes gram per kilowatt hour. Other way we can represent as emission index with respect to fuel flow rate. So, that is gram per second by kg per seconds. So, here in the same way we have called as SE or EI. SE stands for specific emissions, EI stands for emission index. So, for SE calculations, the denominator part as brake power, and for EI calculations the denominator part as mass flow rate of the fuel. And of course, we have whatever emissions you require, the numerator contains the similar terms. For example, if you require the specific index for NOx, then we can have mass flow rate of NOx in the calculations. So, likewise appropriate expressions can be utilized. Okay. So, with this we conclude this talk and or some this particular topic. Now, we will try to see some numerical problems. So, here we have emphasized two topics, one is exergy, other is emissions. So, the first problem is based on the engine based on the calculation of exergy from the exhaust of the engine. So, as you see the schematic of this figure, we have this engine cylinder. So, we can say the charge comes in, fresh charge comes in, and here the exhaust product or we say combustion product goes out. As a result, we produce shaft work W. So, what is the question given? That we have gaseous combustion products which is at 7 bar and 847 degree centigrade in the engine cylinders. So, engine conditions are arbitrary conditions as P as 7 bar, temperature as 847 degree centigrade, or we can say this is about 1120 degree, this is 1120 degree centigrade. Okay. Now, since we are going to calculate the specific exergy. So, to start the solutions, first we can say the assumption that we have used is closed system, and for the combustion products we say the combustion products behave as ideal gas, no change in kinetic energy and potential energy, and last one we can say dead state, which is environment. So, dead state means it goes to atmosphere, and this dead state as P naught as 1.013 bar and T naught as 300 Kelvin. Okay. So, with this assumption we are going to calculate the specific exergy. So, specific exergy mathematically we can write E as U minus U0 plus P0 into V minus V0 minus T0 S minus S0 plus kinetic energy plus potential energy. So, as I say, this goes to 0 and this also goes to 0, that is change is 0. Now, let us evaluate each term. To evaluate each term, we require a data table. So, from any thermodynamic book, we can get the data for air, that is ideal gas, and the data that you require, the temperature, internal energy, because these expressions are required, these values are required, and entropy. So, here we have two temperatures, one is 300 Kelvin, where internal energy is 214 and entropy is 1.7 kilojoule per kg Kelvin. 1120 Kelvin, this value is 862.8, and that is internal energy, entropy is 3.09. So, this data is required. In addition to that, we require R bar by R bar, that is universal gas constant. 8.314 kilojoule per kg Kelvin. Molecular weight for air 28.97. So, we have all the data. Now, let us see how we are going to calculate. So, first u minus u 0. So, this becomes 8. So, this is u, this is u 0 and this is u. So, this becomes difference between these two is 648.8 kilojoule per kg. Then P into V minus V 0, that we can calculate as taking this as taking V as R bar by M T by P and V 0 as R bar by M T by P 0, T 0 by P 0. So, P minus P into V minus V 0 becomes R bar by M into P 0 T divided by P minus T 0. So, this will give you P into V minus V 0 happens to be minus 39.6 kilojoule per kg. Now, next term is T S T 0 into S minus X 0. So, that expression is T 0 into S 0 at temperature T minus S at temperature T 0 minus R bar by M ln P by P 0. So, this particular expression you can get from the entropy difference from the book, and we can put it here. So, all the numbers are given, entropy values are given here, and when you put it, T 0 into S minus S 0 term becomes 0.84 kilojoule per kg Kelvin. So, we have all three values u minus E 0, P into V minus V 0 and T 0 into S minus S 0. So, finally, when you put this term in this first equation, then the E value will be 648.8 minus 39.6 minus sorry. So, this value is T 0. So, 300, that is T 0 into S minus S 0 into 0.84. So, E becomes 357.2. Specific energy is 357.2. So, it means close to 357.2 kilojoule of heat or exergy is available in the combustion products. So, if it is utilized properly, we can get back some energy out of these combustion products. Now, we will move to next problem, that is on engine emission. So, a given question is that we have a 12 cylinder engine, 2 stroke CI engine that operates at 550 rpm to produce brake power of 2450 kilowatt, and it uses stoichiometric diesel fuel. So, the engine has a bore of 240 mm and stroke of 320 mm with volumetric and combustion efficiency as 98%. So, you have to calculate the mass flow rate of fuel into engine, specific emissions of unburned gases and emission index. So, the solution that we can start. So, to start the solutions, first we have to give the because we require the volumetric efficiency and combustion efficiency, we also require mass flow rate of air. Mass flow rate of air can be calculated from its volumetric efficiency, that is eta V density of air into displacement volume V d into RPM divided by small n, that is number of revolutions. So, this is the expressions. So, we have to find out V d displacement volume, that is required number of cylinders into pi by 4 B square S. So, B is given 240 mm, S is 320 mm. So, 0.24 meter, 0.32 meter. Number of cylinders K is 12. So, we can find out V d as 0.1737 meter cube, and we can take the data for density of air as 1.18 kg per meter cube. So, from this we can find out mass flow rate of air. Volumetric efficiency is given 98%, 0.98, n as 550 rpm, small n is equal to 2. So, by putting these values here, we can get mass flow rate of air is 0.92 kg per second. So, mass flow rate of fuel can be calculated, and it is a stoichiometric light diesel. So, we can say mass flow rate of air divided by air fuel ratio. Air fuel ratio in this case we can say 14.6. So, we can write 0.92 by 14.6. So, we can get m dot f as 0.0634 kg per second. Okay. So, this is about all the data given. Now, let us come back to first answer you get the mass flow rate of fuel. Second is specific emission of hydrocarbon. So, for the second question we can write what is hydrocarbon left unburnt, that is nothing but 1 minus combustion efficiency into mass flow rate of the fuel. So, 1 minus 0.98 and mass flow rate of the fuel is 0.0634. So, this turns out to be 1.27 gram per second. Okay. Then we can calculate specific emission for hydrocarbon fuel, that is nothing but m dot unburnt divided by W dot B brake power. So, this is 1.27 gram per second into 3600 second per hour. I have multiplied intentionally because we need to represent as in 2450, that is brake power. So, this turns out to be second gets cancelled. If you calculate this is about 1.86 gram per kilowatt hour, because this, since that is the reason it was converted into second per hour. So, this is how the specific emissions for hydrocarbon fuel, and last part is emission index EI for hydrocarbon fuel. So, here we have to take m dot unburnt and the denominator you have to write m dot fuel. So, m dot unburnt is 1.27 gram per second divided by m dot fuel we have 0.0634 kg per second. So, this ratio becomes 20 gram per second divided by kg per second. Okay. So, this is how we can calculate the specific emission and emission index for hydrocarbon fuels. Okay. With this I conclude this lecture for today, and also we have completed the module 3, that is IC engines internal combustion engine part. Thank you for your attention.